Hello, everybody, and welcome to Lecture 3 of our Calculus 1 class. So today we're going to be talking about the product rule for differentiation. So that's the derivative of the product of one function with another function. And we're going to be also talking about the chain rule, which is how to get the derivative of a function composed with another function, which I'll remind you what that means in case you forgot. And then we'll also be taking derivatives of other functions that we have not yet taken the derivative of. And one essential character in the history of what we're going to be talking about today is this gentleman, Gottfried Wilhelm Leibniz, who I've mentioned before. He was big on the idea of infinitesimals, and in fact he has a book on the ultimate philosophy book on metaphysics, which is sort of like, if you're unfamiliar, sort of like the ultimate nature of reality, and called the monadology. And he has this idea of how everything's made up of monads, and you can see the similarity with infinitesimals. I mean, he doesn't assert that an infinitesimal is a monad, but you can see how, if you're interested, you can look at it. You can just search Leibniz monadology PDF. I find point 14 particularly interesting. So Leibniz. So going back to yesterday, if you remember the limit rules, we had the rule that if limit as w approaches x of f of x and limit as w approaches x, g of x, if both of these limits exist, then the limit as w approaches x of, these should be w's, taking limit as w approaches x. Limit w approaches x, f of w, limit as w approaches x of g of w. Then the limit as w approaches x of f of w times g of w equals the limit as w approaches x of f of w times the limit as w approaches x of g of w. And so if you remember, from the limit rules, we had some corresponding differentiation rules. So one might suspect, and this is actually what Leibniz asserted and later regretted asserting, quickly fixed, but what one might naively expect if one didn't know better, as Leibniz didn't know better when he first said this, is that you have a corresponding rule that would be, so I should say, caution, not true. Just don't put this in your notes as a true statement, because it's not true. One could expect that perhaps f of x times g of x prime equals f prime of x g prime of x. But, as I warned you, this is not true. You might ask, well, why is it not true? Well, maybe the better question is, why is it true? Why would it be true? It's not true. Because if you actually go through and write out the limits, it doesn't follow. Now, of course, if f was just a constant, and we just had some constant times g of x, then it also would not. It would be problematic, because this would be 0, and we know the correct rule for a constant multiplication, and it doesn't always make the function vanish. So, what is the actual rule? Well, I'll start with a more visual diagram. So, say we have a rectangle, and let's rename the variable, the independent variable, to be t for time, so that we can more easily imagine that this thing is growing over time. So let's say that the base of this rectangle is f of t, and the height of the rectangle is g of t. Then the area of the rectangle will be f of t times g of t, right? Because that's what an area is. An area is the product of the lengths of the two sides of a rectangle. So now we have a visual representation of this function, and as g of t grows, we have this face moving outwards, and as f of t grows, we have this whole face moving outwards, right? And then we have this corner, which, as in the case when we did this for a similar, remember I drew a similar picture earlier for taking the derivative of x squared, as we've in both of the last two lectures looked at. This is going to end up being negligible. But if you just intuitively, if you think about the fact that g is changing at a certain rate, but this area is changing at the rate that g is changing times this length f. So we get f of t times g prime of t for this change. And then for this change, we have a height g multiplied times the change in f, right, for this rectangle. And so we get plus f prime of t times g of t. And the product rule is that f of t is g of t, the derivative of f of t times g of t is going to be f of t times g prime of t plus f prime of t times g of t. And that's the product rule, and I encourage you to write everything out in the limit if you want to. If you like the rigor, you can prove it by writing out the limits. So that is the product rule. So at this point, we can prove the power rule on that basis, which the power rule is that x to the n prime equals n times x to the n minus 1. Now, notice yesterday when I was talking about this power rule at the end of last lecture, I made a little mistake, and I forgot to put the minus 1 here, even though if you followed my algebraic manipulations, it was clear that there should have been a minus 1 because we had all these bracketed expressions, right? And we picked a single h, so we have to end up with n minus 1 x's because there are n expressions, and we get rid of 1 for the h. But anyways, so there was a typo on that. In this version of it, we don't need to worry about all the bracketed expressions. This is actually a much simpler version of the proof, I guess, from an algorithmic standpoint. So, we can prove it using something called induction. So, which most of you probably haven't heard, and that is okay. If any of you go on to take discrete math, you'll learn more about it. But the idea is basically that we can prove, by proving it for smaller powers, we can immediately prove it for bigger powers. So this is the power rule, and let's start by finding the derivative of x to the fourth. X to the fourth derivative by the product rule is going to equal, well, first of all, I'll write that this is x times x cubed derivative. And then by the product rule, we're going to take the derivative of this one and multiply it times this function. So x derivative times x cubed. And then we're going to add it to this function times the derivative of this function. So x times the derivative of x cubed. Now, this derivative is just 1, right? The derivative of x is just 1. So we proved yesterday. We get 1 times x cubed plus x times, this one's going to be, the derivative is 3x squared plus x times 3x squared. And this is going to be 4 times x cubed. And then we could similarly, using this expression, if we wanted to take the derivative of x to the fifth, everything would go through basically the same. We would just replace this with 5, replace this with a 4, and then this would be replaced with a 4, but then we just found, and this again would be replaced with a 4, but then since we just found the derivative of x to the fourth, it's 4x cubed, we would put 4x cubed right here. And this, of course, would be x to the fourth. And we would get 5x to the fourth. Notice we're adding, we have this one from the previous step, and then from the previous thing we derived, and then we add this, which is always just going to be 1 times x to the fourth, or in the last case is x cubed. So you can follow through this reasoning, and I won't go through and define the principle of mathematical induction, but it's pretty much a fancy word for something pretty common sense. I guess it seems common sense to me. Maybe I've just been studying math too long. And if you want, you can think about it some more. I encourage thinking about it some more, but it's not essential. That this reasoning will tell you that n x to the n minus 1, that is the derivative of x to the n. And maybe I'll show you one more step in it, and showing this is because you're getting x prime times x to the minus 1 plus x times x to the n minus 1 prime. With this one, we will have already known in advance. So like before, when we computed the derivative of x to the fifth, we already knew what x to the fourth was. Then we did that, we found out what x to the fifth was, and then we could go on and find out what x to the sixth is, then x to the seventh, and x to the eighth, and x to the ninth. We could just go on and keep doing that until we got them all. Give me any number, and we could get to it by just taking steps over and over again. So again, the rule is okay. So another limit rule that we had before that we might think. So when Leibniz first put forth the erroneous claim about what the product rule is going to be, he then quickly revoked it and then proved that correct rule that we just did. But then there's also a quotient rule. So you remember we had a rule for the limit of the quotient, assuming that they both exist and are not both 0. We had the quotient limit law, the limit law for a quotient. And you might, I won't even suggest that you might think that would be a differentiation rule, because with the product rule we already learned that we shouldn't assume that all the limit rules give us differentiation rules. So the quotient rule for derivatives, the derivative of a quotient of functions, is I don't know of a good picture for it, or I do know of a picture I like, but it requires concepts that are not presented in this class, so I don't really know what else to do than to give a full on limit algebraic presentation of it. So hold on to your hats. I guess this makes up for the fact that we didn't get to do so with the product rule. Of course, it would have actually been easier with the product rule than with the quotient rule, but hold on to your hats. We're going to do a full-on limit derivation here. So this derivative we can write out as a limit and go ahead and cross multiply here, as tends to be a thing to do when you're adding or subtracting fractions. Then all over h, but then we can just put that in there. And the next step is a little bit of a tricky step, I guess you could say. We're gonna add f of x times g of x minus f of x times g of x. Which of course f of x times g of x minus f of x times g of x is 0. And that's maybe a reason that a lot of people resent math, is that we do things like add 0 to an equation when 0 is just expressed in some fancy way, and then all of a sudden everything works out. But that's essentially what's going to happen here. So I'm going to rewrite this equation with in the numerator here. We're going to add f of x times g of x minus f of x times g of x, and we're not changing the expression at all because all we're doing is adding 0. So this equals f of x plus h times g of x minus, as I said, f of x times g of x, and then minus f of x times g of x plus h plus f of x times g of x. And all, and I'm forgetting the limit sign. This is all over h times g of x plus h times g of x. Well, before I write the next line, I should explain why I did this this f of x times g of x minus f of x times g of x thing. So the reason I did it is because now we can do this. Minus and minus is a plus. So we put this in parentheses with the minus, and we're good. So then we think, okay, why did we do that again? We did it because of the factoring. So then maybe that helps. Still probably annoying. It probably still seems like it came out of nowhere. But if you do enough algebraic manipulations for long enough, you start to understand the method behind the madness for when to do that type of thing. But even then, I mean, there could be some way that turning zero into some bizarre expression will do some wonderful thing that you would never expect. But then we can factor a g out of these first two terms. So this part right here becomes g of x times f of x plus h minus f of x. And this was our real hidden motivation, is we're going to pull the h up here. into the numerator. And then pull the f out to the front here. And again, g of x plus h minus g of x. The h again pulled into the numerator, or into the denominator of a fraction that's now in the numerator. And then all of this is still over g of x times g of x plus h. Okay. So now we can use all of our limit laws to pull this limit into here, and separately into here, and then separately down here, because this doesn't equal 0. And we're going to get an expression, but I have to erase everything. So take this in, and or you know what? I'll leave this at the bottom and just curl around on the top to this whole thing equals g of x times limit h approaches 0 f of x plus h minus f of x over h minus f of x times limit h approaches 0 g of x plus h plus g of x h all over the limit as h approaches 0 of g of x plus h times g of x. And of course, now it becomes clear that we've actually been making a few assumptions all along. We've been making the assumption that, well, in order to get to the next step that we want to get to, we've been making some assumptions which I'll now state what those assumptions are. And that is, one, we're going to assume that g of x is continuous, so that this limit, and of course, as I mentioned before, we assume it's not 0 for the whole thing to make sense, but we assume that g of x is continuous, so that this will just become, we can evaluate the limit in the denominator, and this will just become g of x squared in the denominator. And then the other assumption we've made is that this limit exists and this limit exists. In other words, that f and g are differentiable, that their derivative exists. And note, Newton and Leibniz and a lot of these earlier people just did basically what I did yesterday, and just say, of course, take the derivative, just basically assume that all functions are differentiable. And I'll give you in a second I'll give you an example of a function which is not differentiable, or which fails to be differentiable somewhere. It's a function you've actually all seen before. But so let's say that f of x and g of x are differentiable, then this equals g of x times f prime of x minus f of x times g prime of x. Okay, so let me re-summarize this. And in fact, I'll summarize the product rule in it as well. So assume that f of x, the f prime of x and g prime of x exist. That is, the limits exist in the limit definition. Then one product rule f of x times prime equals f of x times g prime of x plus f prime of x times g of x. It's the product rule and the quotient rule. If furthermore, and if furthermore, g of x is not equal to 0, then quotient rule the derivative of f of x over g of x is f of x times g prime of x, sorry, g of x times f prime of x minus f of x times g prime of x all over g of x squared. So that is the product rule and the quotient rule. And so I said that there's some content to the assumption that that the derivative exists. And it seems like, well, the derivative is a tangent line. I mean, there's always a tangent line, right? Well, sometimes there's actually not a tangent line. And a familiar example is the absolute value function. So here, there isn't really a tangent line, or there's several tangent lines. You can touch the graph in all sorts of different ways. The tangent line is not well defined, is the way that it's said. And algebraically, we can prove that as follows. So let's try to take the derivative of this at 0. So of course, away from 0, the derivative does exist. It's just the slope of the line. But let's try to take the derivative at 0 of the absolute value function. So limit as h approaches 0 of the absolute value of 0 plus h, absolute value of 0 plus h minus the absolute value of 0 all over h. Of course, this is just phony to put the zeros in there. So we can get rid of the zeros and we have this. But this limit doesn't actually exist because the right limit, we evaluated this yesterday, remember the right limit is 1 and the left limit is -1. So it's not differentiable, which makes sense because there's not a tangent line right here. It could be anything. Okay, so, or we'll say for now that it's not differentiable. So where the derivative does exist, it's this -1 and +1. The slope on one side is -1. Slope on the other side is +1. If you get into advanced enough level of math, you would say that the derivative is this, and then the derivative of this thing is some very strange thing called the Dirac-Delta function, but that's not for our purposes, the derivative doesn't exist in that case. So there we do. I mean, for the most part in this class, the derivative will exist. You won't really have to worry about, wait, I'm doing the quotient rule, does the derivative actually exist? You won't generally have to worry about that. But if we want to be completely formal and correct, then we need the assumption that that both functions are differentiable whenever we apply a rule that involves multiple functions. Okay, so before we dive into the chain rule, because that's going to be a whole other ordeal, let's take a break and evaluate a couple new derivatives. So the quotient rule gives us the ability to take the derivative of 1 over x. I mean, we could actually also do this via limits. It would be easy enough. But derivative of 1 over x is going to equal g is x g times the derivative of f, which is f is 1, minus x prime times 1 all over x squared. Well, the derivative of a constant function is 0, remember? I mean, the tangent line's horizontal, has slope 0, or you can do the limit either way. Is 0, so this term vanishes, and the derivative of x is 1, so this just becomes 1. And the final answer is negative 1 over x squared. This, if you look carefully at it, you will realize that this is the power rule in a certain, it still is the power rule, which is sort of cool, because this can be rewritten as negative x to the minus 2. And so this statement right here this can also be rewritten as x to the minus 1. So this is the power, an instance of the power rule again, because negative x to the minus 1, or sorry, x to the minus 1 equals negative 1 times x to the minus 2. So we again have the power rule. This is again with n equals minus 1. And actually, we could do this with an arbitrary n here, arbitrary whole number, n, whole non-zero number. And we would use the quotient rule again, so that f is still 1, g is x to the n, so g is x to the n, and then multiplied times f prime, so 1 prime, of course it's nothing but then minus the derivative of g, which is n x to the n, times f, which is just 1, and then we put it all over g squared, which is x to the n squared, also known as x to the 2n. Doesn't matter because half of it's going to disappear anyways immediately. The n up here is going to cancel with the n down here when you divide through. So we end up with negative n over x to the n, or in other words, negative n times x to the negative n. I've used a notation where I'm assuming n's positive, but I mean you could just say if n, instead of assuming n's positive, we were to or if we rewrote n to be say r, then this tells us that what we've shown so far is that, so slightly more general, power rule. X to the r prime equals r x to the r minus 1. Now note r, what I'm writing now for r here was negative n in the example we just did, but it could also be positive n for the other ones we did. So this holds for r equaled any negative integer, so I'll write that as these commas, -3, -2. And these dots here mean any whole number less than -4. -1 or 1, 2, 3. Now, notice that I did not include 0 in here, so we haven't shown it for 0. And in fact, it's not true for 0, because the derivative of 0 is just a constant function, and the derivative of 0 is just 0. Or sorry, x to the 0 is just a constant function. The derivative, so x to the 0 equals derivative of x to the 0 equals the derivative of 1, which just equals 0. And this is not the power rule because 0 is not equal to 0 times x to the minus 1. Because 0 times x to the minus 1, that would be 0 over x. And when x is 0, this would fail to be defined. So that isn't any good. So the power rule we've shown holds for all negative whole numbers and all positive whole numbers. It will actually turn out to hold for non-whole numbers as well, and we'll get to that either today or next time. But so far we've only been dealing with these power functions, and of course we want to get to some other functions. So let's go ahead and do some other functions. So first, I will visually demonstrate the derivatives of sine and cosine, and I'm going to be a little bit loose about the limit taking process, but everything I'm saying is true, and if you were to, and I'll also include a Desmos graphic, but if you were to look and think very carefully through the order in which I'm taking the limits, of course everything I'm saying would be true, but of course you might just have to trust me because this introductory course, to really mathematically very rigorously prove everything takes some more technicality than I'm sure most of you want to get into, and the ones you do want to get into it will go on and take more advanced math classes. But so let's say we have a right triangle in the unit circle, which is of course what we have when we're dealing with trigonometry. It's not a very good vertical line. And then, so this, remember, theta in radians, theta is going to be the length along the unit circle here. And say we change the length by h. So h is the change in theta. This is not very helpful because this is a curvy triangle, a curvilinear triangle, and we don't really know anything about those. But if h is small, this is just a right triangle. If h is arbitrarily, if it was infinitesimally small, it would be a right triangle. But it becomes more and more like a right triangle as h gets smaller and smaller. So we're just going to draw this as a right triangle for the sake of our diagram. And so the new height, so the initial height is sine of theta. So this height right here, this is sine of theta, right? And the new height is going to be sine of theta plus h. It's going to be this height right here. So how would we compute that height? Well, okay, so this is pi over 2. Right angle is pi over 2 in radians. Of course, it's 180 degrees in degrees, but in radians it is pi over 2. And then this angle, all the angles of the triangle have to add together to pi in radians. It would be 180 degrees in degrees, but it's pi in radians. So this angle right here is pi over 2 minus theta, because that's what it would take in order for all these things to add up to pi. As you can check, now they all add up to pi. And for clarity, let's call this angle phi. and we denote this angle with 2 lines and this angle with 1 line. Okay, so now we're going to do some angle addition type arguments that you saw in high school geometry in order to determine what this height is right here. This height, sine of, I'll go ahead and erase the rest of the circle since we're not using it, sine of theta plus h. Because sine of theta, remember we're trying to figure something out about the change. And I promise it'll come full circle to the derivative fairly quickly. I mean, when we think change, that's what the derivative is all about, is change. So the angle here is changing. So sine theta plus h equals sine of theta, this height, plus this other height. So let's draw a little line here. Oh, and this will be a right angle, we can see. So it's going to equal sine of theta plus this other little height that we'll get to soon. Okay, so now similar triangles. So hold on to your hats. This we're going to have to draw in this very tiny picture. So this right here, this is a right angle, right? Because this is a vertical line intersecting a horizontal line. So since this is a right angle, or actually, let's start with the fact that this is a right angle. The opposite side of it's supposed to be a right angle. It's sort of bad picture, but this is a right angle because this is a vertical line, this is a horizontal line. Okay, and so this angle plus this little angle right here have to add up to pi over 2. Well, that means that this angle right here is theta, which we denote with the 1/, as you may have done in geometry class. But then this is a right angle too. This right here, the angle between these 2 lines. So this angle plus this angle needs to add up to pi over 2. That means that this is going to be phi, which we denote with 2 slashes. And that means that this angle right here is going to be theta. And that is the angle we really wanted, because now this triangle, this is a triangle with right angle, is a right triangle with angle theta right there. So that means, we're turned on our side here. So that means that that this length, this is adjacent, right? Because we're turned on our side here. So this is the adjacent, and this is the hypotenuse. So the height of this triangle is cosine of this angle. This angle with the 1/ is theta. So the length of this segment is h times cosine of theta. This is h times cosine of theta. So, okay, so we have this expression. And why exactly did we want this expression? This is technically approximate, and this approximation gets better as h goes to 0. So the reason we wanted this approximation is because we can rearrange it into before I write the limit bar, I'll do sine of theta plus h, subtract sine theta from both sides. Sine of theta plus h minus sine of theta. And then this will be approximately equal to h of cosine theta, and then divide both sides by h, and limit as h goes to 0. As h goes to 0, it goes to equality, and we see that the derivative is that this is the derivative of sine theta. Equals cosine theta. Now, by looking at this diagram, we can see that this length right here, this is negative sine theta. So we immediately have another differentiation rule, which is that cosine of theta prime equals negative sine theta. And like I said, I included a Desmos graphic, so in case you couldn't really see what's going on here with the dashes, there'll be a Desmos graphic and you can zoom in and look at it carefully. See how this process is working. So with those differentiation rules in hand, let's go ahead and compute some more interesting, derivatives of trigonometric functions. So derivative of tangent theta, well, this is the derivative of sine of theta over cosine theta. So quotient rule, we have cosine theta times sine theta prime minus sine theta times cosine theta prime, all over cosine theta squared, which is often written cos squared theta. Cos squared theta. But really this means cosine theta squared. And then using the differentiation rules that I just erased, this is the derivative of sine is cosine, so this is cosine squared theta minus, and then the derivative of cosine is negative sine theta, so it's going to be minus sine theta times negative sine theta, so the minus signs cancel and we get plus sine squared theta over cosine squared theta. And of course, Pythagorean identity, this is just 1. Cosine squared theta plus sine squared theta equals 1. It's the base and height of a triangle. The squares of the two things added together, it's a hypotenuse, it's the unit circle, so it's 1. So, and this can be re-expressed secant theta squared, which again is often written with the exponent right there for whatever reason. So that gives us another differentiation rule, and we could similarly do the same thing for the various other trigonometric functions. I'll put those as review problems for the coming test. Yeah, so we can do a number of derivatives now using the quotient rule and the product rule. Yeah, so let's move on to another type of function to take derivatives of. So recall a function like 2 to the x, f of x equals 2 to the x. And well, what is this function? So two to the first power is just 2. Or 2 to the first power is f of 1 is 2. F of 2 is 2 squared, so that's going to be 4. And then f of 3 is going to be 8. And it's going to be all the way up here. So, and then 2 to the 0 is 1, anything to the 0 is 1. And then 2 to the minus 1 is 1 over 2 to the 1, which is 1 over 2, 1/2. 2 to the minus 2 is 1/4. 2 to the minus 1/3 is 1/8. So these are getting very small very fast. And for a function in general, this can also, we can fill in the curve for values other than integers. course, that makes sense. So, for example, this right here, this is going to be the square root of 2, right? 2 to the 1/2 is going to be the square root of 2, which is approximately equal to 1.4 something. It's sort of embarrassing. I don't even know the next digit of the square root of 2. But it's something of 4, 1.4 something. So yeah, so we have this function. It seems like a function we might want to take a derivative of, because why not? It's another function. And so right again, f of x equals 2 to the x, and then f prime of x equals the limit as h approaches 0 of 2 to the x plus h minus 2 to the x over h. And we can factor out a 2 to the x, right? Because there's an exponent. There's a rule whenever you're dealing with exponents that 2 to the a plus b equals 2 to the a times 2 to the b. It for whole numbers it makes sense, right? Because if this was, say, 2 to the 3 plus 5, then that's the 2 multiplied times itself 8 times, which is certainly the same as 2 multiplied by itself 3 times 2 multiplied by itself 5 times. And then it's also true for these non-whole number values as well. So we can factor out a 2 to the x. We get 2 to the x out in front of the limit times limit h approaches 0 h approaches 0 of 2 to the h minus 1 over h. Okay, so this right here, this limit, it's not immediately clear how to evaluate, but it doesn't involve x, so that's sort of interesting. So this function is kind of like it's its own derivative. And for the moment, let's call this quantity right here L of 2. So what this tells us is that f prime of x equals L of 2 times f of x. And that's kind of interesting. But we could also notice that we could replace 2 with 3 or 2.5 or 5 or 2.6 or 2.78. 2.78, I'm getting at something. So you'll see soon what's special about 2.78 and infinitely other repeating digits. But we could replace this with anything else, and all of the same rules would any other positive number. Negative numbers we'd have big problems. We'd replace it with a, some positive number a, and everything's all the same. And let's call this now L of a. So it'd be L of a. So okay, this L function is sort of enigmatic. I mean, what do we do with L? But the significant point is that we can, and of course, this L function. I mean, it's not immediately clear that the limit even exists, because this goes to 0, right? As h goes to 0, a to the h goes to 1, right? Because a to the 0 would be 1. And of course 1 minus 1 is 0, and h is going to 0. So both of these things are going to 0. So it's not immediately clear that the limit exists, but I'm going to tell you that it does exist and it's a certain function. And furthermore, I'm going to assert that, and actually, so to see that the limit does exist would, to visually see that the limit does exist, we could go back to the graph of our function of f of x equals 2 to the x. So L of 2 is, if we set a equal to 2 here, L of 2 is the derivative of this function at x equals 0, right? So the fact that this function has, just by looking at the curve, we can see, well, there is a derivative, there is a well-defined slope, and that slope is L of 2, or if this was, f of x equals a to the x, then this slope right here, slope equals f prime of 0, right? Because if x is 0, this is just 1, and we get f prime of 0, just equals this limit right here, equals L of a. So the limit does exist, and we can see it in that way. And furthermore, I'm going to assert that there exists some special number such that L of 1 equals, such that L of this number equals 1. And this number is called E. So L of E equals 1. And this implies that e to the x, the derivative of e to the x, equals L of e times e to the x, which is just e to the x. Yeah, so this is pretty interesting. It's a function which is its own derivative. Yeah, so that's kind of cool. There's a whole field actually called differential equations, which is like algebra, only you have a equation instead of an equation like a polynomial that relates the unknown variable x. You relate a function to its derivative, and so this is a function which satisfies what's called a differential equation, f prime of x equals f of x, which is pretty cool, pretty interesting. And of course, the value of this function, or the value of e is approximately equal to 2.78, some other stuff. But again, it's an exponential function, so it's going to look pretty similar to the function we had before, the 2 to the x. It's going to be a similar looking curve. And this is called Euler's constant. E is short for Euler. I don't really have any historical notes about Euler. He did so much that it's hard to really say anything about it. But one of the things he did was involving this number. He also did a lot of stuff with fluids, the mathematics of fluids, and all sorts of things. Yeah. So we have this function e to the x, which has itself as its derivative. And now maybe it would be worthwhile to relate L to e to the x so you can get a better sense of what L is, because L seems somewhat uncomfortable. So L of e to the x equals limit as h approaches 0 of e to the x to the h minus 1 over h. And again, another rule for exponentiation, which you can think of in very similar terms to the last rule I told you about, is that when you exponentiate something that's already exponentiated outside of the parentheses, you can just multiply the exponents. And so now, I don't know why I had the parent there, it should have been there. So now we're going to do something that I don't think we've done before, but it's a fairly simple concept, which is that if h approaches 0, then xh also approaches 0 because x is a fixed number in this case. You know, insofar as the limit's concerned, it's a fixed number. I mean, still, it's in the function, but as far as the limit's concerned, it's a fixed number. And so we're going to do something called a substitution. But first of all, we're going to multiply this times x. And we're going to do the substitution k equals x times h. So then we have limit k approaches 0 of e to the k minus 1 over k, or sorry, over k over h, right? Because h is actually, h is, sorry, k over x. So h is k over x, dividing both sides of this by x. And of course we multiply both sides by x. So what that will do is these two x's will cancel. And we'll just have an x in the denominator. And this right here, it doesn't matter that we've renamed k to be, or sorry, that we've renamed k, hx to be k, still the limit of something going to 0, e to that something minus 1 over that something. So it's the same as if k were still h. It's, so far as this limit's concerned, it makes no difference. And so this is L of e, right? But we already know that L of e is just 1. Right, so this is just x. And so what this tells us is that L is the inverse function of e to the x. E to the x and L of x are inverse to each other. And the name that L of x is given is actually usually ln x. So, yeah, and the ln stands for log natural. And in older textbooks, you'll just see it written as log x, which, please pardon me if I should just say, and I should just say up front that ln x and log x are the same, because I'm not going to be able to help myself. I'm so used to doing log x that at some point as I'm talking about ln x, I'm going to drift into log x. But I'll explain to you the reason for its name, as well as the reason why certain authors prefer to call it lnx as opposed to log x. And the reason is, if you remember from algebra, you probably learned about log base. So like log base 2 of 8 is 3. And what this says is that you would need to multiply, you need to raise 2 to the third power in order to get 8. So what this log is it's the inverse function of the of the function 2 to the x. Log base 2 of 2 to the x equals x. And so natural log of e to the x equals x, right? Because this is what I was calling capital L now. What I was calling capital L before, I'm now calling ln log natural. And so this could actually be written as log base e of x. Log base e of x. Yeah, and something, because of calculus and the stuff we've been talking about, some people seem to think of this base as being particularly natural. I don't know. I still think log base 2 or log base 10 are really the most natural as far as I'm concerned. But for calculus purposes, this is pretty natural, and so they call it the log natural. So, so in summary, we have e to the x is a function with e to the x, derivative of e to the x equals e to the x, and ln x is the inverse of e to the x, so ln of e to the x equals x. And another property of L, how we first introduced L, if you remember, is that, or as we're now calling it, ln, is that 2 to the x prime equals ln of 2 times 2 to the x, or actually in general, a to the x prime equals ln of a times a to the x when a is a positive number. So I said in the beginning that I was going to do the chain rule as well, but then in thinking about it, I realized that presenting yet another new thing before the test is probably not a good idea, even though it's a summer class and it's fast. I probably shouldn't throw yet another thing on all in one day before a test. So I'm not going to do the chain rule. Instead, I am just going to compute a couple examples of what we've talked about previously in this lecture. So putting things together, let's compute a more weird sort of function. Let's take the derivative of sine x over e to the x minus x squared tangent x. Now, this, you can see how we're starting to, as we learn these rules, we're able to start building things up that we can solve, which, in mathematics there's, and in science in general, in fact, not just mathematics, in the sciences in general, there's a saying that you don't solve the most interesting problems, you solve the problems that you can solve. And so finding the derivative of this, so this, if you look at how I've cooked this up, I've cooked it up very intentionally to be something that we can solve given everything we know, because we know the derivative of this function, we know the derivative of this function, we know the derivative of this function, we know the derivative of this function. We know how to take the derivative of the quotient of two functions that we know how to take the derivative of. We know how to take the derivative of the product of two functions. We know how to take the derivative of. And lastly, and of course, obviously, we know how to take the derivative of the difference of two functions that we know how to take the derivative of. And in fact, just to make this complete in terms of making use of all the rules we know, I'll put a 5 in there. Because remember, when you multiply a function times a constant and take the derivative, it doesn't, it just pulls right out to the front outside of the derivative. Okay. So derivative of this, quotient rule, and the derivative of sine of x is cosine. So first we have e to the x times derivative of sine x minus derivative of e to the x times sine of x all over e to the x. E to the x squared. All of this minus 5. The 5 pulls out to the front, as I just said, as we learned before. 5 times x squared times the derivative of tangent of x plus derivative of x squared times tangent of x. Okay, so, wow, this is a lot of stuff. So this, we can simplify and take our derivatives. Let's see, can you see that? Simplify and take our derivatives. So the derivative of e to the x is just going to be e to the x. And the derivative of sine of x is cosine of x with e to the x cosine of x minus e to the x sine of x over e to the x squared. But then there's e to the x on both of these, so one of the two e to the x terms down below gets canceled with, and the other one remains. And then over here, we have 5 times x squared derivative of tangent. The derivative of tangent, if you remember from before, is secant of x squared, or as the notation goes for whatever reason, so x squared times secant of x squared, and for whatever reason, the notation we write secant squared of x. Don't ask me why people do that, but they do. I think it I mean, I guess I do know why they don't want to write the parentheses, so yeah, so secant squared x, and then plus this term, which is 2x times tangent of x. So there we go. There is a good example of a derivative that makes use of all of the rules that we have covered so far. I think. Am I missing any? That's pretty much all of them. Yeah, so you can expect probably to find something like that on the test, a problem that makes use of all the rules. So another derivative we can take, which is sort of I guess you could call it a rule. It'll cease to be a rule next week when we do the chain rule. It'll just be an example of the chain rule. But present it now just to expand our arsenal of things so we can differentiate a little bit. And what it is e to the ax. So let's take the derivative of e to the ax. This is going to be We can factor out an e to the ax for both of these. And when we factor out the e to the ax here, we're just left with an e to the ah, and here we're just left with a 1. And then we're going to do substitution again, like I talked about before with limits. And our substitution is going to be k equals k equals ah. Which means that h equals k over a. Divide this up for this. And we can pull out the a to the front, multiply this times a over a, and this gives us e. These a's cancel, and this gives us a times e to the ax times, this a e to the ax times limit as k approaches 0. You probably can't see that. Let me continue it over here. Let's do that. Limit as, e to the a, e to the ax times limit as k approaches 0 of e to the k minus 1 over k. But this term right here, that is, if you recognize it, it's just the derivative of e to the x at 0. This equals e to the x prime evaluated at 0, which is just 1. So this first term is just 1. And so in summary, e to the ax prime equals a times e to the ax. And then go ahead and give an example of this. So let's say we want to differentiate x to the n times, and I'll set n equal to 5. X to the 5 times e to the minus 3x. Then we can just use the product rule. A e to the ax, and a is minus 3, so it'll be minus 3 times e to the minus 3x. And as far as homeworks and tests are concerned, this is a perfectly good answer. But a lot of us just feel like the compulsive desire to simplify everything. And of course, we could factor out an x to the 4th times e to the minus 3x. times 5 minus 3x. Yeah. So there's another example, and I'll give you more examples in the review sheet for the test. And something that's kind of cool about this rule is it, if we were to have something like sine x over e to the x, this we look at and we're like, oh, I have to use the quotient rule. And the quotient rule has a whole bunch of parts to it. But fortunately, because of the rule that we just learned, this, of course, is just, dividing by e to the x is the same as multiplying by e to the minus x. So this is the same as e to the minus x times sine x prime. And so we can just use the product rule now, which is nicer than using the quotient rule. It's just going to equal minus e to the minus x sine x plus e to the minus x cosine x. Yeah, and I guess that's probably enough for today. I'll attach some resources. I'll attach a worksheet. I'll attach the Desmos visualization for the trigonometric derivatives, and I'll also attach a review worksheet for the test, and maybe I'll see some of you in office hours, and otherwise Monday. So have a good day, and best wishes for the test.